Hello and welcome to this video. My name is Matthew Bauchi from the Physics of Amorphous and Inorganic Solid Laboratory at UCLA. And this is the first lecture for CEE 206, which is Modeling and Simulation of Civil Engineering Materials. This is a class that is open to both undergraduates and graduate students here at UCLA. It's designed to give you an introduction on what are the typical modeling and simulation techniques that can be used to simulate materials, and especially materials that are relevant to civil engineering, so glasses, metals, concrete, etc. It's a class that, as I mentioned before, is open to both undergraduates and graduates in the sense that I will try to provide you with all the necessary background information, all the prerequisites that you need to know to understand this class, even if you know fairly little in material science and engineering. You should be able to understand the content of this class and more importantly, to be able to learn how to use some simulation tools to conduct different types of simulation to predict the behavior of materials, whether it's atomistic simulation, mesoscale simulation, or continuous simulation. If you need to contact me regarding questions regarding this class, you can contact me at bauchi@ucla.edu, which is bauchy@ucla.edu. So today we are going to review what will be the goal of this class, what we are going to see during this quarter, and to start to see a first introduction of a few definitions that will be useful to understand the content of this class. Specifically, we are going to talk about what is a model, what is a simulation, how does it differ from a theory or an experiment, for example, and how is it useful to access or predict the properties of materials. So what is the goal of CEE 206? Well, so we have different goals with this class, and this class ideally should be useful to different types of students who have different types of objectives that are related to simulation and modeling of materials. The first goal of this class is to try to explain and demystify what simulations are, why are they useful, and what can you use them from, but also what are their limitations, what can you not do using simulation. The idea is that there is some level of misunderstanding, in the sense that some people who are not aware of what is the idea behind simulation may think that it might just be some numerical result that do not have any experimental relevance, or would not be relevant to real experimental system. On the other hand, it's very easy to just be fully convinced about simulation, about their power, and to just trust simulation too much, and to just use them and to trust their result as being a reference, and without having any doubts on what could be their limitation. So it's important to understand what is the main theory behind different types of simulation, to understand what are their strengths, what is their use, and also what is their limitation. The second thing, besides this theoretical aspect of this class, is to really learn in practice how do you implement and run different types of simulation, and how to visualize the outcome of different types of simulation. In this class, for example, we are going to focus on the LAMPS package, which is a package that you can use to simulate to conduct some molecular dynamics simulation, to simulate the motion of atoms in materials, and also to simulate, for example, to conduct some Monte Carlo simulation or some peridynamic simulation. So we are going to focus on this LAMPS package because it's fairly common package to simulate materials at different scales. It's a pretty popular package. It can be used for a wide variety of application, and so we are going really to focus on this package and to learn how to use it, to understand what are the different possibilities offered by LAMPS, and how it can be useful to implement advanced simulation, to simulate different type of behavior of different types of materials under different conditions. The third thing is really to choose how to approach a given problem. If a problem cannot be tackled by conducting experiments or by doing purely theoretical calculation, and if it appears that simulation offer a useful approach, then we still need to understand what is the right approach, what is the right method to tackle each problem, and what is the right scale of interest for a given problem. For example, if you want to simulate the behavior of a bridge, then certain types of method and certain types of skills will be appropriate to simulate these types of problems. For example, if you want to simulate the behavior of a bridge, then it's a continuous problem. So you will have to use methods that are relevant to continuous material, for example, finite element simulation or peridynamics. And in this case, the right scale will be meters or potentially kilometers if it's a very long bridge. So every time you want to conduct a new simulation, you always need to ask yourself, what is the right scale that will be the relevant scale to describe the behavior of the material that I'm interested in? And what is going to be the right method? What is the right theoretical background? Is it continuous material, the continuous mechanics? Is it the theory of how atoms interact with each other? Is it, do I need a subatomic theory taking into account quantum effects? Do I need to account for relativistic effects? So every time you want to simulate a given problem, you need to look at what is the right theoretical background that you need, and different types of problems, even for the same material, will require different method and different scales to be applied. And the last thing is to give you some background for people who may not be in the future using simulation, but still need to understand the existing literature and the papers that have been published on a given topic that are simulation based. The idea is that if you are conducting primarily experiments, you still need to be able to ideally understand like what is the main idea behind simulation work that are relevant to the kind of research that you are doing. What is their strength? What can we learn from them? What is the limitation? So the idea is that this course should give you the necessary background that is needed to understand the simulation papers that are relevant to your field and understand what you can learn from them, but also potentially identify potential weakness in those papers based on the model that is used and the types of method that is used. So the content of this class will be primarily twofold, in the sense that a fraction of this class we really focus on some theoretical background. For example, we will need to review what gives rise to the cohesion of material, what makes material cohesive. Materials are made of atoms. Why are those atoms sticking together? Why are they not separating from each other? What makes atoms attract each other? What are the different types of energy that bonds atoms together? It's essential that we review those things to be able how to simulate the behavior of materials and how to simulate, for example, how atoms interact with each other, how atoms want to remain bonded. For example, if you try to extend a given material to measure its Young's modulus, if we want to simulate this at the atomic scale, we need to know what are the fundamental forces that are attracting the atoms with respect to each other. And the second aspect of this class is more practical, how to implement those theoretical aspects that we are going to review in practical simulation. So in this class, most of the homework that you will have to do will be about running practical project, so small simulation project. Each homework will be a small simulation project where either you will have to code yourself some simple algorithm to solve a given problem, or you will have to use existing package, especially LAMPS, to solve different types of problem applied to different types of materials and different types of properties and different types of conditions. So this is really the two main goals of this class, to give you the right theoretical background to understand what material simulation are about, but also to teach you how in practice to conduct those simulations. So this class is basically a theoretical and practical introduction to computational material science. But what is computational material science? So this is what we are going to talk about today in this first lecture. We are going to see some basic definitions to try to make sure we all agree on what is a simulation, what is computational material science, what is a model, what is an experiment, what is a theory. So all those words, what do they mean? How do they relate to each other? What are the different relationships, the different linkage between those different approaches? And how can they be useful to each other? How can they advance and inform each other? This is what will be the focus of this first lecture. So the first question that we are going to ask is, what is an experiment? What does it mean to conduct an experiment for a given materials? So the first thing to be sure we understand is that running an experiment, when you run an experiment, what is the goal of an experiment is to assess the behavior or the properties of a given system or given materials. But when you do this, experiments are always going to assess some signature of materials and some response of materials, not the material itself. For example, if you want to assess what is the elasticity of a given materials, you cannot just look at the material and assess its elasticity. What I mean is that if you want to assess the stiffness or the elasticity of a given material, you will need to apply a stimulus. For example, you will need to deform the material, apply a given deformation, and measure the response of the material, measure the corresponding stress that you need to apply. Or you will need to apply a given stress, a given load to the material and measure its corresponding strain deformation. So when you conduct an experiment, you never directly look at the system or directly look at the material. You always apply a given stimulus, a given excitation, a given input, and you measure a response of the material. So to summarize this, the key thing to remember is that the material or the system that you are trying to try to describe or to try to further understand. So this is, for example, this system can be a given material, a given structure, or any kind of physical or chemical system. This system is always invisible. For example, if you want to measure a given property of the material, it's not enough to directly look at this material. You have to test it, and to test it is to conduct an experiment. How do you conduct an experiment? You don't look at the material itself, it's invisible, but you apply a stimulus. So you apply a given input. This input depends on the type of behavior that you are trying to assess. If you want to assess the stiffness of a material, you will need to either apply a load to the material, or you will need to deform the material. If you are trying to measure the transparency of a material, then you will need to apply an incoming source of light. If you are trying to measure the durability of a material, then you are going to try to put this material in contact with water. If you are going to try to measure the heat capacity or the thermal expansion of a material, then you will need to apply a source of heat to increase the temperature and see what will be the corresponding response of the material. So this is the second thing, is after you have applied a given stimulus, a given input, you are going to measure something. So you are going to get a response from the material. So you are going to get an output. Again, in the case of, for example, the calorimetry experiments, you will either provide some heat and measure the change in temperature of the material, or you will provide a change in temperature and measure how much heat was used by the material to increase its temperature. This will provide you the heat capacity of the material. Or you will apply a change in temperature and measure the change in dimension of the material to measure its coefficient of thermal expansion. Or you will provide a given load and measure the change in dimension to get the Young's modulus, for example. or provide a deformation, a change in dimension, a strain, and measure what is the resulting pressure of the material, again, to get its elasticity, its stiffness. In any case, the key thing to remember is that an experiment is never going to see directly the material itself. It's always going to test the response of materials to a given stimulus and get a response of materials that then can be used to characterize, to compute the properties of materials. And the properties are what is relating the input to the output. Then what is a model and why do we need models to begin with? So why do we need models? Because real materials, real systems are complex and they are usually too complex in order to study them. Why are materials complex? First, they are complex because they contain a lot of, the materials themselves are complex. They have a complex structure. They have complex behaviors. And the second reason is that they are governed by complex physics, like some physics that we don't necessarily understand. For example, if you're trying to predict what is the corrosion rate of a given material, we don't necessarily understand enough about what is really the physics that is governing the corrosion, the dissolution of materials in contact with water or in contact with atmosphere, the weathering of material is something we just don't understand enough about the real physics. So the real physics that is governing materials is always too complicated, so we need to model it. And materials themselves are usually also too complicated. Systems in general are too complicated and they need to be simplified in order to be able to understand and predict what is their behavior, their properties, their response to given inputs. So this is how we can summarize what a model is. A model is necessarily going to be a simplification of a real system. Real systems are too complex. So if you want to make some predictions and to gain some understanding about the behaviors of materials and systems in general, you need to simplify them in a way that you capture what is important and filter out what is less important. So for example, let's look at this map here, which is the map of Boston. If you look at this kind of map here, so this map is a representation of a real system in all its complexity. It's a picture. You take a picture from a satellite of Boston and you see all the details of all the complexity of Boston and its neighborhood. This is a very accurate representation of the real system that Boston is, but it's not usable if you want to make some prediction of, for example, how fast will it be to go from point A to point B, or how can I go from point A to point B? Why? Because this system is too complex. You have too much information. You have all the details of all the buildings, of all the streets, and it's not something that you can use in practice to figure out how to go to point A to point B, what will be the easiest way, what will be the fastest way, or how long will it take. On the other hand, if you want to be able to use this and make some prediction regarding this system, you will need some models and you will need to simplify. What does it need to simplify is that you will keep only the features of the system that are relevant, the one that are governing the types of problem that you are trying to solve, and you will try to filter out the details that do not matter. So the details that don't matter depends on the system, on the problem that you are trying to solve. For example, if you are trying to figure out how you will be able to go from point A to point B using a subway, what is the subway line that you are going to use, how many stops do you have to take before, or what is the best line, where should you change, etc. Then all you care is really the subway network, and you don't care about the rest, you don't care about the streets, etc. But for other types of problems, if you are trying to, for example, measure the distance between 2 points, or if you are trying to figure out what is the fraction of Boston that is covered by forest, or if you are trying to to understand what is the population of Boston, what is the density of buildings in Boston, then other types of details will matter, and maybe the subway lines in this case will not matter. So you start from a very complex system like this map of Boston, and then depending on the problem that you are trying to solve, certain feature of this complex reality will be relevant and some others will be less relevant or completely irrelevant. And most of the time, if you want to solve a complex problem, you cannot consider the whole system in all its complexity. You need to simplify it. You need to keep only the relevant features that matter, that will have an influence on the types of problem that you are trying to solve. So for example, in this case, if you are trying to figure out how to go from point A to point B using the subway, a first level of simplification would be to try to get rid of all the pictures of all the buildings within Boston, but to really focus on the transportation network and to have a map that shows only the subway lines and the given stops. But even these types of maps features too much complexity, because you have all the shape of all the lines, you have all the distance between each stop. You have all the other streets, all the main streets that are available, and you don't care about this level of complexity. You don't care about seeing exactly what is the shape of the subway line, where does it turn, where is it a straight line. You don't care necessarily that the distance between those two stops here is shorter than the distance between those two stops. All you care is which line should you take, where should you change from one line to another. And if this is the only information that you care, then you can go to another level of simplification where you just make an even simpler representation of the subway network, where, for example, you just assume that all the stations are equidistant from each other, like you just represent all those stations as being equally far away from each other. You don't care about the actual shape of the path that the subway is following, so you just represent them as a straight line. And this is increasing visibility. This is making it easier for the reader to understand what is the path, where should it change from one line to another. So when you try to solve a problem like this, you will necessarily need to simplify the system, and you will need to make a representation. So this is a gross representation of reality. This is a simplification. You're making some mistake. You are representing this map of Boston, which is not accurate anymore. It may not be the right distances, but it's a simplification that allows you to solve the problem that matters to you, which is to figure out how to go to one station to the next. So when you're trying to solve a given problem, you will necessarily have to make some assumptions, some simplification. So you will not be studying the real system in all its complexity. And the point of finding the right model to simulate a given problem is to find what is really the key simplification that you need to make. What are the key relevant features that you need to conserve from the system that you are trying to understand, and to keep only those features that really are key to solve the problem that you are trying to solve, and to filter out the rest of those features that do not matter and just make the system more complex and make the solution of this problem more difficult to achieve. So in summary, we can provide the following definition for our model. We can follow the definition from Professor Asby from Cambridge University. So in this case, for example, if you take the example of the Boston map, the map obviously misrepresents the distances between stations and the directions. For example, it doesn't consider all the turns of the subway, but it focuses on the connectivity between the lines, which station are connected with the same lines, or how many changes between different lines do you need to make in order to reach one station to another. So when you build a model, you will necessarily misrepresent certain aspects of reality, but you will focus and capture the key relevant features, which in this case is the connectivity. So the quality of what makes a model useful or not useful is really its ability to govern, to capture the features that really govern the types of problem that you are trying to solve, and to filter out the rest. So a good model can be a very distorted representation of reality. Sometimes you can have a model that really misrepresent a lot of the features of reality, but as long as it captures really the features that really matter for a given problem, then that can be a good model. So you can have different types of modeling. Sometimes models are based on the physics of what you understand from the given problem. For example, if you are trying to understand the elasticity of a given material, then you know that certain materials that can be described by the Hooke's law, so they can behave like a spring. So sometimes you know some knowledge about the physics that is governing a given problem, and that can be used as a key ingredient of your model. Sometimes you don't understand anything about the physics, and you will just rely on data. You will rely on existing data that are representing the behavior of a given system, and you will use those data in order to build a model that ignores everything about the underlying physics that is governing the behavior of the system that you are interested in, but it's just based on existing data. So in any case, models can be based either on those data and ignore everything about the underlying physics. This is the data-driven model, like for example, a model based on machine learning or regression. And you can have models that are based more on knowledge rather than observation. So those can be physics-driven model, chemistry-driven models, etc. And the key thing is that once you have a model, and once you can make sure that a model accurately represents reality for the types of problem that you are trying to solve and to understand, then the key thing is that once you have made sure that under certain condition your model works and is in agreement with observation, then you can use this model to understand the response of system, the response of materials to new conditions that have not yet been observed, not yet been studied. For example, if you use a model to predict what is the elasticity of materials for different types of deformation, different types of temperature, if your model is correct, you can validate your model for certain types of temperature, certain types of loads, and then use your model to extrapolate and to predict what will be the behavior of your materials if the composition of the material is changing, if the range of load condition is changing, if the temperature is changing. The idea is that if you build your model in a way that it can represent reality in a convincing way, then it means that this model is capturing the right physics that is governing the behavior of materials, and then you can use this model to extrapolate and predict the behavior of materials to new conditions that either have not been explored yet or cannot be explored because of experimental difficulty, for example, raising high temperature, materials under irradiation, or high pressure conditions that are not easy to achieve from an experimental viewpoint. So to summarize, a model is necessarily a simplified description of a real complex system. This simplification is key to be able to solve a given problem, either analytically or using simulation. The key thing is that a model should be able to capture the essential physics that is governing the behavior of materials, to really capture and embed what are the key features of the material that will impact its response under certain conditions, but to filter out the details that do not necessarily matter for a certain types of system under certain types of conditions. For example, we know that all systems to some extent are made of atoms, and those atoms, the way they interact with each other and the way those atoms are made of, those are some quantum effects. But in many cases, the quantum description of how atoms are made of and interact with each other does not necessarily matter the macroscopic response of materials. So in this case, all the quantum effects about the cohesion of atoms and the way they interact with each other does not necessarily matter. It can be filtered out, and you can focus on what are the key physics that is governing atoms interacting with each other, or the key physics governing the behavior of continuous solids. And this is the only thing that you will keep within your model in order to predict the macroscopic response of systems. The first thing to remember is that whenever possible, you should always make sure that a given model matches with experimental observation. If you have some experimental observation, then you need to make sure that your model does not contradict experimental observation. Otherwise, it means that probably your model is either not valid or is maybe too simple. Maybe you have filtered out too much details and you have lost some of the complexity of certain types of materials and certain types of systems. But in any case, if your model does not agree with experiments, then either there is something about the experiment that you are not understanding properly, either your model is not correct or too simple. And once you have a model that agree reasonably within the accuracy that you are willing to accept with experimental observation, then you can use it to extrapolate the response of systems and materials to new conditions that either have not been accessed yet or are just simply inaccessible to conventional experiments due to reasons of cost, reasons of feasibility, or reasons of convenience. So let's take another example to illustrate what a model is. So for example, let's assume that we want to simulate the dynamics of three bodies interacting with each other. For example, you have the sun. So let's assume that we have the sun here and that the sun is interacting with the earth. So we have another body which is the earth, and the earth is interacting with the moon. So we have a third body which is the moon. So here, if we want to simulate or to model the behavior of those three bodies and how they are going to interact with each other, what will be the dynamics of each of those three bodies, then the first thing is that if you look at this system, even this simple system cannot easily be treated directly if you consider all the complexity. If you take a picture of the system, then you will see the sun. The sun is made of certain types of materials. It is not homogeneous. It is mostly spherical, but maybe not exactly spherical. The earth, similarly, is made of different types of materials as a function of how deep you go. It is not a perfect sphere. It has all kind of complexity. Same thing for the moon. It has a given geometry, given types of materials. Now, if all you want is to predict in a fairly accurate way the trajectories of those three bodies according to time, you don't need to consider all this level of complexity. You can rely on a simplified model that will be a representation of this complex system into something that is more usable, a more simpler form that can be used to actually simulate or to calculate analytically the behavior of these materials. So the first thing when you build a model would be to try to simplify the system that you are trying to understand. So for example, this is in this case the real system, those three bodies in all their complexity. If you want to understand and predict the dynamics of the system, you will rely on a model, and a model will be a simplification of this complex system. So you can have different types of model with different degree of complexity depending on how you are planning to solve and to study the dynamics of those free bodies. If you are planning to conduct a simulation or to simulate or to calculate analytically the dynamics of those free bodies, you will need different degree of simplification. The first degree of simplification that you will probably want to do is to consider that those free objects are not heterogeneous but rather homogeneous with a given density. You will maybe want to consider them as perfect spheres rather than more ellipsoid objects. Or even better, maybe you will consider that the distance between those objects is large enough that the size of those objects doesn't really matter. Maybe all that matters is the mass of those three objects and not necessarily their size. Of course, this level of simplification depends on the type of problem that you are trying to simulate. For example, if you are trying to simulate the problem of tides and why the ocean is going up and down on Earth, then it would not be acceptable to simulate Earth as a single mass point or as a perfect sphere. You will need to go in and take into account an additional level of complexity. But if the only thing that you are trying to do is to simulate what is the motion of the Earth around the Sun, then it's probably fine to simulate the Sun as just one point where you have a mass that is concentrated, which is equal to the mass of the Sun, to consider that the Earth is also a mass point that corresponds to the mass of the Earth, and that the Moon is another point that corresponds to the mass of the Moon. In this case, what you consider is that the size of the objects do not matter. Why? Because those objects are sufficiently far enough from each other that their actual geometry doesn't matter and they can be approximated as points. And you will assume that in this case, representing this system of free bodies is enough to be treated as points if you don't care about their own rotation. For example, if you just care about their relative motion, then probably simulating them as points is a reasonable starting approximation. So that's the first thing, is you need to simplify the actual system, which is always too complex to be treated differently. The second thing that you will need to simplify also is what is the governing physics? What is the theoretical background that you are going to use? Again, this level of the physics that is governing system is always too complicated, either because we don't know enough about the physics, either because what we know about the physics makes it impossible to be analytically calculated or even simulated within a reasonable computing time. So for example, here, when you will need to describe what is the physics that is governing the interaction between those three bodies, you have different options. For example, you could decide to treat this with general relativity or restricted relativity, but in this case, so you will end up with a very complex problem where you will be able to treat relativistic effects, but maybe, again, if you are trying to just simulate the motion of the Moon around the Earth or the motion of the Earth around the Sun, maybe relativity doesn't matter. In this case, maybe just using the classical laws of mechanics, the Newton laws of motion, will just be enough in order to simulate this given system. So for any given problem, you need to find what is the right theoretical background, what is the right level of complexity that is needed to have an accurate description of the system that you are trying to understand without having unnecessary complexity that will make it impossible to solve the problem that you are trying to solve. So for example, in this case, we are going to say that we are going to just use the framework of the Newton's law of motion and disregard any relativistic effect between those three bodies. The second thing is, even after you have chosen the right theoretical background that is the right level of accuracy and the best balance between accuracy and complexity, you will need to decide what are the assumptions that you are making. What are which phenomenon are you willing to consider? Which one are you going to try to solve, and which one are you going to try to neglect? For example, in this case, a common approximation to try to solve these types of problems, to try to numerically predict the behavior of those free bodies, is to say that we are going to neglect some of the interaction between certain bodies within the systems. Why is this needed? Because even for a simple system like this of 3 points, it cannot be solved directly analytically without making a certain number of assumptions. This is a classical problem that the free body problem cannot be solved analytically. It can be solved fairly easily using simulation, but not directly with pen and paper calculations. So for example, here, the assumption that we can make is that we are going to neglect the interaction between the moon and the sun. Why? Because we are going to consider that the interaction between the sun and the earth and the interaction between the earth and the moon is much more, has a higher magnitude than the interaction between the moon and the sun. So we are going to consider the interaction between the sun and the earth. Why? Because the earth has a much higher mass than the moon, so its interaction with the sun will be higher than the interaction with the moon. And we are going to disregard the interaction between moon and sun at the expense of the interaction between earth and moon. Why? Because the earth and the moon are much closer from each other than the sun is from the moon. Okay, so this is a common assumption that in this case we are going to disregard the interaction between the sun and the moon and only consider the interaction between sun and earth and moon and earth. So this is an example of the level of simplification that you will need to do when you are building a model based on the types of problem that you are trying to understand, or based on the types of behavior that you are trying to predict. You will need to understand and to figure out what is the right level of simplification that I need for the system itself, for the physics that is governing this system, what are the key features that I need to keep, and what are the key features that I can filter out that do not really matter, that do not significantly govern or do not have a significant effect on the behavior of the system that I'm trying to study. Once you have done this exercise, then you will end up with a given model. And this model, if simple enough, you will be able to solve it analytically and to predict, for example, the motion of those three bodies according to time. Or if the model is too complex to be solved analytically, then maybe you will be able to solve it numerically by conducting a simulation. So what exactly is a simulation? How is it different from experiments? How is it different from theory? How is it different from a model? So here we are going to talk about computational material science, so the different field of simulation applied to materials and to understand the behavior and the physics of materials. So computational material science is really a third branch of material science. So you have experimental material science, where you just test the behavior of material that are subjected to different types of stimulus. Then you have the theory, which is just an ensemble of laws that are governing the physics of behavior. For example, the theory of gravitation, the theory of relativity. Those are an ensemble of laws that are enunciated to describe the general behavior of certain types of system and certain types of materials. And then in between these two things, or as a separate field, in addition to experimental and theoretical computational material science, then you have computational material science, and you have simulation, which provide an additional pathway to predict and understand and explore the behavior of materials. So the first thing that we need to make clear is that a simulation is different from a model. A simulation is not a model. A model is not a simulation. But you always need a model to conduct a simulation. So what is a simulation? A simulation is just an algorithm, a numerical method that is used to numerically solve a complex model that would otherwise not be solvable analytically. For example, if you still take the example of those free bodies that we talked about, if you do not neglect the interaction between the sun and the moon, then you are not able to solve analytically the model. So you can just write the Newton's law of motion applied to the moon, applied to the earth, applied to the sun, and you will see that you cannot solve this problem analytically, but you can solve it in a numerical way with a certain level of accuracy that can be tuned based on how much computing power you have. So it's important to make this distinction between model and simulation. Simulation needs a model. You need to start by creating a model, a simplification of reality. And then once you have the model, either you can solve it analytically or you cannot. And if you cannot, then you can try to solve it in a numerical fashion. And that's what a simulation is. A simulation needs a model, and the simulation is an algorithm, a numerical algorithm, a numerical recipe that can be used to numerically solve a given model based on certain assumptions that are contained within the model. So how do you conduct a simulation? A simulation is an algorithm. What is an algorithm? It's a series of instructions. So it's like a recipe. If you are trying to cook, you are going to heat the food at a given temperature for a given time. So it's a series of instructions, do this, do that, a series of instructions that can be executed by a computer. And the main idea of a simulation and algorithm in general is that if you directly look at the series of instructions themselves, you cannot predict the outcome of the simulation. What the outcome of the simulation can only be predicted if you are conducting this simulation. For example, if you just look at a recipe book to cook different materials, if you just look at the instruction, mix flour with water and eggs and heat it for this amount of time, then bake it, and then etc. You cannot predict what this is going to give you. You cannot predict that this is going to give you a cake or anything like this. In order to get the cake, you actually have to conduct this recipe, to follow the recipe, to follow the algorithm, to follow all the types of instruction. And this is what an algorithm is. The value of an algorithm is that it can be executed and it gives you an outcome, and you would not have been able to predict the outcome of the simulation just by looking at the instruction itself. If you were able to predict the outcome of the simulation just by looking at the instruction, then there is no use for the simulation. You could have just predicted directly, analytically, the outcome of the simulation. The value of the simulation is to be a series of instructions that are always the same, whatever are the parameters of your problem. The parameters can change. The instructions are always the same. And the outcome that your algorithm will give you, the instructions are always the same, but the outcome can be different based on the different parameters or the different inputs that you are trying to use as a base for the series of instructions that your algorithm comprises. So why do we need to rely on simulation? Because model cannot always be solved analytically. Whenever models can be solved analytically, this is preferable to just rely on an analytical solution because it's going to be more accurate than a simulation. But most of the time, the laws of nature or the real system that you are simulating are just too complex to be solved analytically. And in that case, it's useful to conduct a simulation that will be able to give you a numerical response of a given model. The main idea here is that if you have enough computing power, you can use a computer. The computer will give you an approximate answer for a given model, and you can always choose the level of accuracy that you want. So when you are trying to solve numerically equation that cannot be solved analytically, for example, the differential equation or a derivative or things like this, or integrals, you can always, if you cannot solve them analytically, you can solve them numerically, and you can solve them with different level of accuracy. You can select what is going to be the accuracy that you are willing to want. And usually the higher the accuracy you want, the more computing power you will need in order to reach this accuracy. Or on the other hand, if you are willing to accept a lower accuracy, then your simulation can be made more efficient from a computational viewpoint, and you will be able to achieve the solution in a shorter time. So you will have this balance between how much accuracy would you like and how long will be the simulation, how much computing time will you need to achieve this solution. So one thing that is good to keep in mind is that computational material science is only like a fairly new field. It's basically, it took rise when computer became more available, which is less than 1 century ago. And before simulation, like the really computational material science did not exist. So every time you had a model that was not solvable in a perfectly analytical manner, then necessarily you had to use some approximation until the model becomes solvable. For example, if you are trying to simulate to understand the motion of bodies, then you would have to, if you have more than 2 bodies, you would have to neglect some of the interaction, just like neglecting, for example, the interaction between the sun and the moon in order to be able to solve it analytically. If you are trying to solve the equation of states for a gas, then you would need to make some assumption, for example, to assume that it's a perfect gas where the atoms do not interact with each other, do not have any size, and will just collide perfectly elastically with each other. You will need to make some assumption to simplify your system until the model can be solved analytically. For example, another example is crystals. If you want to predict the heat capacity of crystal as a function of temperature, you can rely on the harmonic approximation. Just assume that atoms are vibrating in a purely harmonic way like a pendulum. And if you are not making those assumptions, then you will not be able to solve analytically those models. So nowadays, when models are not solvable analytically, you can conduct simulation. But before the rise of computers, it was impossible to run simulation. So necessarily, you had to simplify models until they can be solved analytically. So now that we understand what's the difference between experiments, simulation, model, theories, etc., it's important to keep in mind that those different objects are not isolated from each other. You always need one to validate the other or to inform the other. So for example, this is a useful diagram to summarize what are the relationship between experiments, simulation, and theories. So you always start with a real system. So for example, here, if we are trying to model the behavior of liquid, the equation of states of liquids, for example, you start with a real liquid, which is a very complex system. If you want to assess the behavior and the properties of liquids, one option, and it's the first 3 here, is that you can conduct an experiment. For example, you can measure the rheology of liquids, you can measure the pressure within a liquid as a function of its volume, etc. So you can conduct some experiments. When you are conducting experiments, you are applying a stimulus, applying an excitation, and you will measure the response of the real complex system that you are studying. You will not necessarily look at the liquid itself, but only look at its response to given stimulus. So you will perform an experiment and you will get a result, the result being the response of the liquid to a given stimulus. For example, you are going to shear the liquid and measure the corresponding force, or you are going to compress the liquid and measure its pressure, or you are going to measure the viscosity of liquid. So you're going to measure the response of the liquids to a given stimulus. On the other hand, if you want to understand more about what is the physics that is governing this liquid, or if you want to understand and to predict the behavior of liquids to new conditions of pressure, of temperature, of shear rates that are not accessible from conventional experiments, then you will need to make a model. So you will need to model liquids in a way that can be solved numerically or analytically. So depending on the level of simplification of your models, maybe you can construct an approximate theory. You can make a lot of assumptions to make it possible for the model to be solved analytically. And if it's solved analytically, then you can make some theoretical prediction. If I neglect these and these features of this complex system, and if I neglect some of if I focus only on certain types of physical behavior of the system, then maybe you can reach a theoretical model that is purely analytical. On the other hand, if you make a model that is easy enough to be solvable numerically but not necessarily analytically, then you can solve this model by using a computer simulation. The computer simulation will just be a way to numerically solve the outcome of a given model for certain types of inputs. And just like you are conducting following a recipe to cook a given dish, you will just use certain inputs, sometimes raw ingredients, and then follow a list of instructions that can be interpreted by a computer and assess what is the numerical outcome of the model. Then you will get a result, the result of the model. The result of the model come with a given accuracy, but it's important to understand that this is an exact result for the types of model that you are considering. The simulation is only as good as the model is. Assuming that you are choosing an accuracy that is high enough, if you are dedicating enough computing time to have an accuracy that is good enough, then the outcome of the simulation will depend only on the assumption of your model. If your model is correct, then the simulation will be correct. The simulation will only be as good as the model. What I mean by that is that the simulation cannot be wrong. Assuming that it is properly coded, a simulation cannot be wrong. The only thing that can be wrong is the underlying model that a simulation is applied to solve. A simulation is just a series of instruction. It's based on mathematics. It's based on numerical way of solving complex differential equation, integrals, derivative, etc. So the simulation itself, assuming that there is no bug in the simulation cannot be wrong. Only the underlying model can be wrong. So for a given model, you will get an exact response of your model by conducting a simulation. So a simulation is a numerical way to assess what is the response of a model that cannot be solved analytically. So then after that, once you have conducting your simulation, you can use it for two things. You can compare it, and you should always do that, compare it to experimental results. For example, if you have a given set of experimental observation of certain liquids under certain condition of temperature, certain condition of pressure, etc., you should always try to build a model that mimics those conditions and make sure that the prediction of your model, in this case, agree with the experimental observation to ensure that your model is validated under certain types of condition. In that case, it means that you can be fairly confident that your model is capturing the right level of physics and the right level of complexity for your system that is really governing the properties that you are interested in, and that your model is filtering out the physical features and the features of your system that do not necessarily matter so much the response and the properties of materials under the condition that you are interested to studying. On the other hand, you can also compare the prediction of the simulation with the theoretical prediction to check if the approximate model that you made by neglecting certain aspects of the problem, certain aspects of the physics that is governing the system, and certain aspects of the complexities of the system that you are interested in studying, you can compare the prediction of the model and the theoretical prediction to see if the approximation that you did to simplify the model and to make it solvable analytically are correct or not. If you get a good agreement between simulation and between your theoretical model, then it means that the approximation that you did are most likely correct. It means that the approximation that you did, the information that you filtered out, the physics and the complexity that you filtered out to simulate, to approximate and to simplify the system are indeed correct. They indeed do not matter in governing the response of materials for certain types of properties and certain types of conditions. So you can use this to test certain types of theories, certain types of approximation. So let's summarize what simulations are and what they can do. So again, the key thing to remember is that it's not correct to say that a simulation is wrong, because a simulation cannot be wrong. A simulation can be more or less accurate, but you can always make it as accurate as possible by just investing more computing time. For example, when you are solving a differential equation numerically, you have different ways with different accuracy, or you can select the level of accuracy that you want. A simulation can always be as accurate as you want if you are investing enough computing time. A simulation cannot be wrong. If the simulation does not agree with experiments, it means that it is the model that the simulation is based on that is wrong. It means that the model that you are using either is not correct, you have made some wrong assumption in the structure of your materials, in the different features that describe your materials, or you have made some wrong assumption regarding the theory that is governing the behavior of materials, or you have forgotten to include certain aspects that are key, or you are just ignoring certain features that are governing the behaviors of materials, certain complexities of materials, certain complexities in their physics, in certain complexities in their chemistry. So your model is either wrong, either is too simple, you have filtered out too much information, you have made too many assumptions that are making your model just too much of a misrepresentation of reality. Okay. But the simulation itself, again, cannot be wrong. It's just a numerical solution of a given model. So the numerical solution itself cannot be wrong. It is necessarily the model itself that is wrong or too simple. Once a simulation and the corresponding model have been shown to agree fairly well with experimental observation, then you can use it for various things. First, sometimes so you can use it to solve models that are not analytical in a way that without the simulation you would never have been able to analyze what would be the outcome of such a complex model. Without you would have necessarily have to do certain types of further approximation to render this model analytical. So a simulation is a useful pathway to explore what is the outcome of a model and to assess its outcome in a numerical fashion. The second thing that you can use simulation for is to compare different models. So for example, if you want to describe the behavior of certain types of materials under certain types of condition, you may have different models available, different competing models based on different approximation, different theories, or different level of representation of what is important and what is not important. And then you can quickly screen and compare those different models, analyze their outcome using a simulation by solving them numerically, and check which one gives the best agreement with experiments in order to check what are the right assumptions, which model is the most accurate representation of reality. So this is useful to assess different competing models and see which one is the most accurate. And once you have found the most accurate model, then it means that you have understood something about the underlying physics that is governing the behavior of certain types of materials under certain types of conditions. The other thing that simulations are very useful to is to access some details of systems that are invisible to experiments. For example, if you are trying to simulate the behavior of liquids, if you are conducting an experiment on a liquid, you can measure for example, the coefficient of thermal expansion of a liquid by increasing the temperature and measuring the change in the volume of the liquid, but you cannot directly access what is the atomic origin of the thermal expansion. What is causing this liquid to expand as you're increasing the temperature at the atomic level? What is at the atomic level responsible for this macroscopic expansion? The only way that you can access this is to build a model that is describing the interaction between the atoms and to perform a simulation, making sure that your simulation indeed predict an expansion of the liquids as the temperature is increasing, and making sure that you have a good agreement with experiments. And once your simulation agrees with experiments, then you can go back to your simulation. And for example, if you are conducting some molecular dynamics simulation, if you are just directly simulating the motion of the atoms, then you will be able to use this simulation to access some details that are not accessible to experiments. You will be able to see directly the motion of the atoms, study the way atoms interact with each other, the distance between the atoms, the angles between the atoms, the way they repulse or attract each other, etc. So you will be able to access some details that would not be able to be visible from conventional experiments. The idea is that once you have created a model that is simple enough and yet complex enough to describe the behavior that you are trying to understand, for example, the expansion of liquids, then you can be fairly confident that you have captured the right physics that is governing the system of interest, and then you can use this physics to access some details that are not necessarily accessible to experiments, and use it to gain some new understanding about what is governing the response of materials, what is governing the structure, the atomic structure of materials, and how this atomic structure is responsible for the properties of materials, for example. Another potential application of simulation is that sometimes it's perfectly fine to conduct experiments in order to measure the properties of materials, but if you can replace experiments by simulation, then potentially you can explore a broader range of simulation in a cheaper, faster, and more convenient way than doing experiments. For example, if you want to study new types of molecules and see if they can be used for drugs, you have millions and billions of possible types of molecules that can be formed. And if you want to study them one by experiments, that would be very expensive, very time consuming. So if you can replace this by simulation and simulate those different molecules and directly use simulation to predict which of those molecules are stable or not, which one have potentially some interesting properties, then you can replace experiments by simulation just as a more convenient way, a cheaper way, and a faster way to investigate a lot of degrees of freedom. For example, another application for this would be if you are trying to discover new types of glasses with a new composition. You have an infinite number of possible composition for glasses. You cannot make those glasses one by one and test them experimentally. In that case, you can do that by simulation. Why? Because simulations are cheaper and faster than experiments, and just replace experiments by simulation. In that case, the benefits of the simulation is not necessarily to access and to understand some details that are not accessible from experiments. It's just to replace experiments and to offer a more convenient way, faster, cheaper way to replace experiments. And the last possible application of simulation, besides replacing experiments or trying to understand some new insights inside the physics governing systems and materials in general, is to extrapolate and to predict the behavior of materials to new conditions that have not yet been accessed experimentally or cannot be accessed experimentally. The idea being that once you have done a simulation that properly predict and reproduce the behavior and the properties of materials under certain types of condition of temperature, pressure, or etc., then once the model is working and is in agreement with experimental observation, then you can be confident that you are capturing the right physics that is governing the behavior of materials, and can use it to extrapolate and make some prediction about what will be the behavior of materials under very high temperature that are not accessible experimentally, or very low temperature, very high pressure, or predict the behavior under irradiation, or those kind of conditions that are very challenging to access experimentally. The idea being that once you have the right model, then you can use it to extrapolate and to predict the behavior of materials under new conditions. Why? Because if you are modeling these types of system and performing a simulation, the simulation itself is just a series of instructions. Those instructions do not change. The only thing that will change are just the input, the parameters. And for example, if the temperature and the pressure are some inputs for your simulation, some parameters of your simulation, you can just change those inputs and repeat the very same instruction and get a new outcome, a new prediction of the behavior of your materials for the new values of those parameters, for new values of temperature, new values of pressure. So to summarize, simulations are really a part of material science that allows you to make some connection between theory and models and experiments. So the typical step that you will typically follow is to start by observing by experiments a given system and to try to build a model, and this model will be a simplification. You will simplify the system itself. You will try to simplify the governing physics that is governing the response and the properties of these materials, and you will build a simplified model, a simplified representation of the problem that you are trying to solve. Then you are going to use to build an algorithm. You will rely on computational science to try to assess what is the outcome of the model by solving it numerically. So in that sense, conducting a simulation and conducting an experiment is very similar. When you're conducting an experiment, you have a real system. You are providing a stimulus, you are providing an excitation to the system, and you are seeing the response of the system. Conducting a simulation is very similar. You have a model, you are providing some inputs for this model, you are going to solve it analytically or numerically, and you are going to assess what is the outcome of this model. So in the same way that the experiments is going to measure the response of a real system to certain types of stimulation, a simulation is going to predict the outcome of a model based on certain types of input parameters. In that sense, you can describe simulation as being a numerical experiment in the same way that an experiment would be to try to investigate the response of a given materials. So once you have built your model, you will conduct the simulation with a given accuracy. You can select the accuracy that you want, and then you will make a prediction, or you will use experiments to validate your simulation. So when the experiments and simulation agree with each other, then you can be confident that your model is indeed correct, contains the right approximation, the right assumption, and then you can use in turn your simulation and your model to make some new prediction about what would be the behavior of materials under new conditions. Or if you have a disagreement between experiments and simulation, then there is two things. It can be due to the accuracy of the simulation itself. So you may need to increase the accuracy of the simulation that you are running. So solve analytically your model in a more accurate fashion, or you will have to refine your model. You will need to refine the assumption and the simplification that you are making. find a more accurate description of the system that you are simulating, or choose a more accurate theory to describe the behavior of the material, to further and more accurately describe the fundamental physics and the fundamental chemistry that is governing the specific properties that you are interested to study for this specific problem. So usually you can construct and establish a simulation by following a few steps, and this is a schematic representation of the different steps that you should follow when you want to implement a new simulation to solve a given problem. So the first step is always to identify what is the problem. What are you trying to solve? What is the specific goal? Are you trying to just predict properties? Are you trying to understand some new physics about the problem that you are interested in? Are you trying to discover new types of materials? Are you trying to understand the behavior of existing materials? Are you trying to understand the origin of certain experimental observation that you are making that do not obey with existing theory? So you need to make sure you are clear about what is exactly the problem that you are trying to solve. Then you need to start making a model. For this, the first thing is you need to understand what are going to be the input and the output of the model. What are going to be the parameters, the inputs of your model, the temperature, the pressure, the composition of the materials, for example, and what are going to be the outputs? What is going to be the outcome of the model? What is going to be the output property that your model will be predicting? So you need to always make it clear that you will need to know what are the three parameters that can be changed and what is the model going to predict. Then once you have identified what is the input, for example, the temperature, pressure, material composition, etc., and once you have predicted the output, which is, for example, let's say you want to predict the stiffness, the Young's modulus of a given glass as a function of temperature, pressure, glass composition, etc., then you need to choose which is the theory that you are going to use. What is the physical mechanism? How are you going to model your system? Are you going to model your system by the laws of continuous mechanics? But in this case, that would not be the appropriate solution because you would not be able to take into account the effect of the structure and the effect of the composition of the materials. Or are you going to use some models about how atoms are interacting with each other? Or are you going to use quantum mechanics? Are you going to use relativity? Which one are the key physical ingredients that you are going to use and to put in your model to understand what is the relationship between inputs and outputs? The simulation will start from the input, perform a series of instructions, a series of operation in an iterative fashion, and then will give you a specific output. Each of those instructions should be based on some fundamental physics or chemistry that is governing the behavior of the system. So you need to select what are the physical laws that you are going to use, what is the right theoretical background that is relevant to the types of problem that you are trying to address. And that's why the very first important thing is to clearly identify what is the problem that you are trying to solve in order then to be able to choose what is the right theory, what is the right theoretical framework that is going to allow you to solve this problem in the most efficient way, but also the most accurate way. Once you have targeted and identify what are going to be the physical mechanism that you are going to model, then you will need to implement a numerical solution to this model. For this, you will need to select what is the precision that you want. So you will need to find what is the right balance between the accuracy of the response that you want and the complexity. The more accurate you want your simulation to be, the more complex it will be, the more time consuming, the more computing power you will need. And the more efficient you want your simulation to be, the faster you want your simulation to give you an answer, then the less accurate the simulation will be. So you need to find the right balance between how much accuracy you want and how much complexity you are willing to accept. Once you have chosen what is the theoretical framework that you are willing to use, what is the level accuracy that you want, then you can construct your model. You can implement your model and implement the assumption that you are willing to make. The first step after that is always a good idea to check the dimension, to make a dimensional analysis to make sure that the dimension of the inputs are consistent with what is going to be the dimension ultimately of the output of the simulation. And once you have constructed your model, once you have chosen how you are going to represent a complex system, once you have chosen what are the right theoretical background that you are going to use, once you have chosen what are the right assumption of what you are going to capture and what you are going to neglect, what you are going to filter out, once you have chosen what is the right accuracy that you want, then you will implement a computer code. You will implement an algorithm, a series of instructions that the computer will be able to follow in order to numerically assess the outcome of the model. Then, after you have written the computer code, then you will simulate, you will perform the simulation to see what is the numerical outcome of the model. You will get an output, you will get some results that you can compare with experiments, and if those outcomes agree with experiments, then you can be sure that the model that you have chosen and the precision that you have chosen are appropriate. If not, then it means that you will need to either refine the model that you are using, change the theoretical background, or enhance the accuracy of the simulation. In any case, it's important to keep in mind that simulation cannot solve everything, and they always have some limitation, and simulation are always as good as the underlying model is. So just to keep in mind the general limitation of simulation are of course not reality, they are a representation of reality. So whenever you conduct a simulation, you should always make sure you validate them with experiments before using simulation to extrapolate and to predict some behavior of materials. Sometimes experiments are just not possible. So in this case, you have to assume that your model is correct and use simulation to see what is the numerical outcome of your model, and you have no way to validate it. It's just a prediction that maybe one day you will be able to validate, or somebody else will be able to validate by conducting an experiment. But whenever possible, simulation should be validated at least for certain conditions with available experimental data, available experimental observations, before you can use them to either replace experiments or test the outcome, make some prediction of the outcome of models under new conditions that cannot be easily accessed by experiments. Another key thing to remember is that simulation will only provide you data. It will provide you some output. It will provide you some intermediate data that capture the relationship between inputs and the output of your model, but it will not provide you an interpretation. So if you are trying to conduct an experiment, for example, to mimic an experiment and then use the simulation to understand about the underlying physics that is governing the relationship between the input and the output of your model, the simulation itself will not allow you to do that. Simulation will just give you some data, and then it's up to you to interpret those data and to make sense of what is the right relevant physics that is governing the behavior of materials. So again, simulation only provides you some data, and it's up to you to make sense of those data, to interpret them, to gain some new understanding, some new knowledge about the types of materials that you are trying to simulate. The second thing is that you should not necessarily always use simulation, in the sense that even if it's possible to simulate a behavior or given types of materials, doesn't mean that it's the easiest way to do it, because sometimes just conducting an experiment is the right way to go. If you are trying to assess what is the property of a given materials, in many cases, just experimentally measuring the response of this material is going to be much more efficient, much more accurate than trying to simulate it. So of course, simulations are useful in many cases, but they are not always useful, and they are not necessarily the best approach in order to tackle a given problem. And the last thing is that whenever you are conducting an experiment, you need to remember that you are solving numerically some equation. So you have different methods to solve in different ways, differential equation, integral, derivative, etc. So you always need to make sure that you are using methods that have the right level of accuracy for the types of problem that you are interested in. Certain types of problem, even a low accuracy will be acceptable, but for some other types of problems for which it's important to have a very accurate prediction, you will need to make sure that you are using very accurate numerical method to solve the equation that you are trying to solve. So you always need to make sure that not only you are using the right model, but you are using the right numerical method to solve the equation of your model. So to finish this first lecture, let's summarize by summarizing the definition of the few concepts that you have seen in this first lecture. So for this, I like to use the definition that are provided by Professor Laser, because I think they are very clear and very accurate description of computational material science in general. So the first thing we saw is what is a model. And a model is an idealization of a real behavior. So it's necessarily an idealization, so it's a simplification, it's an approximate description that is based on some kind of empirical or physical reasoning. The idea is that either if you have a given behavior, you would just look at certain types of observations, certain types of data, and build an empirical model that is not based on your physical understanding of the problem, but just based on looking at data, observation. For example, if you look at an apple falling from a tree, then you can look at 10 or hundreds or thousands of apples falling from the trees, and just look at how fast do they fall, with what kind of velocities, and try to learn from those observations to build a model that is only based on observation. So this is an empirical model that can be used in the future to describe the motion of apples falling from the trees, even though you don't understand anything about the real physics governing the fall of an apple from a tree. Or you can base your model based on your physical understanding. If you know the Newton's law of motion, then you can build a model that predicts what will be the motion of the apple, its velocity, its acceleration according to time as it is falling from the tree. So you are building a model that is an approximation of a real behavior with some level of assumption, some level of approximation based on existing data or based on existing knowledge, physical or chemical knowledge about the types of problem that you are trying to solve. Then once you have the model, either it can be solved analytically or it cannot. In that case, you can use simulation to solve it numerically. So a simulation is a numerical study of the response of a model to an external stimuli. So you will use a given model once you have the model, and to assess what is the outcome for certain types of stimulus. For certain types of input parameters, you will simulate what your model is predicting the output to be. So you can perform simulation by subjecting the models to different types of inputs and different types of constraints that simulate real events. So that is to say that once you have a model describing the behavior of interest to you, then you can change the inputs of your model or the types of constraints, and you can use your simulation to assess numerically the outcome of your model in a way that can be compared with experiments. Then simulation in general can be categorized as being part of computational material science. So computational material science can be defined as being the ensemble of all the computer-based techniques of modeling and simulation that can be used to understand and predict material behavior. So it's a little bit more general than simulation itself. It's really everything that is computer-based that can be used to assess the behavior of materials. And finally, a theory is an attempt to find the fundamental description of a physical process. For example, theory of gravitation, theory of relativity. This is an ensemble of mathematical equation, an ensemble of concept that can be used in a self-consistent way to describe physical process in general. Okay, so for example, the three laws of motion of the three Newton's law of motion. This is a series of concepts, a series of ideas, a series of equations that describe a physical process, which is different from a model, which is going to be a simplification of reality. So that's it for this first lecture. So there is no homework due now. So the next step that we are going to see in the next lecture is to try to see a first example of how to model a complex physical phenomenon and how to build a model that is simple enough and yet accurate enough to describe and predict the outcome of this physical phenomenon, and then to see how to assess the outcome of this model in a numerical way. So thank you for listening, and see you next time for the next lecture.